We're in section 9.3, two dependent samples of matched pairs. Inferences on matched pairs data is very similar to inferences regarding population means. The next page, on page 7, it says testing hypotheses regarding the differences of two means using matched pairs designed with the DI-83 or 84 calculator. So we can use the following steps provided that, and the three things that you have to have is both are simple random samples, the sample data are matched pairs, and differences are normally distributed with no outliers, or the sample size is large and is greater than 30. Step 1 is determine your null and alternative hypotheses. I want you guys to realize that there's mu sub d, and that says up here where mu sub d is the population mean difference of the matched pairs data, because they're matched up either against themselves or somebody like their child or their spouse. You can subtract the means and it means something. Okay, the next is select alpha, which is again usually given to us. And since we subtracted our numbers and we put that into, that's just a single list of numbers, that means that we can just use what we used last chapter for this, which is t-test. And when you do this, you're going to get two output values again, the test statistic and your p-value. And then it says if the p-value is less than alpha, reject h naught, and then we're going to write a conclusion. And if the sample is small, less than or equal to 30, there's some instructions of how you would deal with that. Okay, we also have confidence intervals, which is another way to do our testing. And this is for matched pairs data. The interval is exact when the population is normally distributed and approximately correct for non-normal populations, provided that n is large. The confidence interval for mu sub d is given by, and we are going to be using t interval under stats and then test, and it gives you the lower bound and your upper bound. So the first example that we have on the bottom of page 7 says, in an experiment conducted online at the University of Mississippi, study participants are asked to react to a stimulus. In one experiment, the participant must press a key on seeing a blue screen. Research reaction times in seconds to press the key is measured. The same person is then asked to press a key on seeing a red screen, again with reactions times measured. The results for 6 randomly sampled study participants are as followed. Note, a normal probability plot and box plot of the data indicate that the differences are approximately normally distributed with no outliers. So since we have a small sample, that had to be stated in there that it's approximately normal. So in order to do this, we are going to, since this is the same person doing the test twice, we're going to find the difference. And you can subtract either way. So I'm going to go ahead and do red minus blue. Again, it does not matter what you do, but I do suggest writing it down so that way you have it and you make sure you are consistent with your subtracting. So if you take a second and you subtract and you do 0.408 minus 0.582, I get negative 0.174. Okay, so take a second and put the rest of the values in. Okay, then once you have those numbers in, and again, you could have subtracted blue minus red, it still would have worked. Your signs would have just been different, but the calculations would have come out the same. So the next thing says, why are these match pairs data? And the reason why is because the same person is being tested twice. The next question says, in this study, the color that the student was first asked to react to was randomly selected. Why is this a good idea? And this is a good idea because it's to control any learning for the exam. And I'll put learning in quotes. So most of the times when you start and you're pressing a button or something along those lines, you're probably not as fast, and then by the end you're getting faster and more used to that test. So rather than to see improvements on the second color, they randomly select it just so then that way it mixes it up. Okay, so the next one says, is reaction time to the blue stimulus different from reaction time to the red stimulus at the alpha equals 0.01 level of significance? It does say different in here, and that's usually a means for not equal to. So since we have this problem, we're going to go ahead and take all of our numbers were back up here in the previous page, and all of your differences, these values down here that we have, all of those have to go in my L1. And when we do that, I want you guys to realize we subtracted and we had a difference. So when we write down our null and our alternative hypotheses, we don't have just mu, we have mu sub d, which is standing for that difference. Your null always has an equal, and I want you guys to realize that it was all equal to 0. And if you think about mu sub d is equal to 0, this means that the difference is 0, meaning that those two values would be the same. And our testing is that they're different, so that would be not equal to 0. And again, we did, our difference was from red minus blue. Okay, so then we're going to go to stats test, and we go to t-test. And we've dealt with t-test before. And again, you have to put all of those d values in L1. Once you have all of that in, calculating your p-value. And again, this is exactly what we used last chapter. P-value is 0.2466, which is greater than our alpha. And if you see our alpha that was back up here, alpha was 0.01. So this is greater than alpha, which is 0.01. And since this is greater, we do not reject H naught. So writing our conclusion for this. So we'll go ahead and say there is not sufficient evidence at the alpha equals 0.01 level of significance to conclude that there is a difference in the reaction time to the blue and red stimuli. There's one more part here. It is part D. And this is about constructing a confidence interval. I'm going to go ahead and circle that and we will discuss